Okay guys, a few people have asked me to clarify in some questions where they take the variance of x, but sometimes they multiply it by the number of elements outside, and sometimes they bring the value inside. I'll explain it here and explain what the difference is in the questions that they give you. This is Mr. Dylanek's example. I don't know where he got it from or whether he made it up himself, but let's have a look. So a machine produces two devices, VINs and Roberts. VINs are produced with a mean weight of 200 grams with 5 grams standard deviations, whereas Roberts have a mean of 400 grams with a standard deviation of 20. They're produced independently of each other and their production weights are normally distributed. A Danuka consists of 4 randomly selected VINs and 2 randomly selected Roberts. Find the probability correct to 4 decimal places that a Danuka, so the combination of these two, will be more than 1.62 kilograms. So in this case here, we have expected value of VINs, which is it 200? We have our expected value of Roberts, which is 400. We have our variance of VINs, which is 5 squared, 25, and our variance of Roberts, which is 20 squared, which is 400. Okay. So a Danuka consists of 4 randomly selected VINs. So that means we grab, I don't know, let's say a VIN's a bottle. We grab one bottle, we grab another bottle, we grab another bottle, we grab another bottle. So there's 4 different VINs and 2 randomly selected Roberts. So once again, we grab 2 different bottles. If I want to work out the expected value of a Danuka, so let's say E of D, that's 4 times my expected value of VINs plus 2 times my expected value of Roberts, which is 4 times 200, 800, plus 2 times 400, 800, so it's 1600. Okay, my variance of D, it's 4 times my variance of V plus 2 times my variance of R, because I've taken individual values, we just multiply the variance by 4. So here we're going to get 4 times 25, which is 100, plus 2 times 400, which is 800. That gives us 900. So our expected value of Danukas is 1600. Our variance, or our standard deviation of Danukas, is going to be the square root of 900, which is 30. To find out that a Danuka is more than 1.62, we use norm CDF 1620, because we've got it in grams, so let's use it in grams. To infinity, because it's more than. My standard deviation is 30 and my mean is 1600. Okay, so let's have a look. Okay, interactive, continuous, oops. What am I doing? Interactive. Distribution, continuous, norm CDF, lower, 1620, upper, infinity, 30, 1600. Okay, 0.2525. Okay, so in that case there, we took 4 different bottles, or I call them bottles, I don't know what they are. I don't know what a VIN or a Robert is. Okay, the weight of a Danuka is estimated by weighing 1 VIN and then multiplying it by 4. So in this case here, my expected value of a VIN is still 200, but my variance, whilst it's still 25, my combination is going to change. So E of R is 400, var of R is 400. Okay, so E of, we can't use D because we used it before, so let's call it D star. That is 4 times E of V plus 2 times E of R, which is the same, 1600. Okay, this time my var of d star is the var of 4v plus the var of 2r, sorry. So here, that's going to be 16 times the var of v plus 4 times the var of r. Can't fit it on the screen. Var of r. Okay, so 16 times the var of v, 16 times 25 is 400, and 4 times 400 is 1600, so altogether that's 2000. So in this case here, my mean of a Danuka is 1600. My standard deviation of a Danuka is the square root of 2000. So our probability is norm CDF 1620 infinity root 2000, and then 1600. So in this case the difference is our standard deviation, so it's root 2000 0.3274. Okay, so in the second case, we're more likely to find that the average that the weights is more than 1.62 kilos. There's a higher probability. Find the average weight of 16 Roberts is less than 396 grams. Okay, so the expected weight of a Roberts is in the sample, it's going to be the same as the population proportion. My expected value, my average value, my weight, so that's 400. My variance of R is, what was it? Sorry, my standard deviation of a Roberts is 20. So the standard deviation of my sample proportion is going to be 20 on root 16, which is 20 divided by 4, which is 5. The average weight is less than 396, so we want to use norm CDF negative infinity 396 5 400. So okay, we'll be saying negative infinity to 396 5 400 0.2119. So that's the probability of that sample of 16 Roberts, that the average weight is less than 396. Okay, second question. The probability density function describes the time in seconds it takes Jack to drink a cup of water from a small cup. Find the probability that the average time will be less than 0.9 seconds if Jack has 6 cups. Okay, so if he has, our expected value is from 0 to 2, x times 1 minus cos pi x on 2 dx. Okay, x. So, integral. What I would suggest in here is don't put the x inside, just put it outside. So x times 1 minus cos pi x on 2. I'll show you why in a second, dx. Okay, so that's 1. So my expected value is 1. E of x squared is the same thing, but it's x squared times f of x dx. Okay, so you just go into here, grab that, just bring it down, so you've got both. Okay, so x squared, negative 2 on pi squared plus 4.3, or 4 on 3. Okay, so we know that our expected value is 1. Our variance of x is e of x squared. So 4 on 3 minus 2 on pi squared minus e of x squared. E of x is 1. So we've got 4 on 3 minus 2 on pi squared. I think that's supposed to be squared, yep. That's going to give us 1 on 3 minus 2 on pi squared. So my standard deviation of x is going to be the square root of 1 on 3 minus 2 on pi squared. Okay, we want to find the probability that the average time is less than 0.9 if he has 6 cups. Okay, so mu is 1. Our standard deviation of our sample, so we'll call it x bar, is the square root of 1 on 3 minus 2 on pi squared on 6. Because we're on the square root of 6 because we want to, that's sigma on root n, that's sigma, that's root n, it's all under the square root. And we want to find the probability it's less than. So we could say x is normally distributed with a mean of 1 and a variance of 1 on 3 minus 2 on pi squared on 6. Looks pretty ugly, but the probability that x is less than 0.9. So we go on to our cas. Okay, so we want to use that value. But let's make that's 1/3. Okay. Distribution continuous. What if we highlight it? Bring it down there. Interactive distribution continuous, norm CDF. Okay, I don't want that value there. I want that value. Stuff it. Okay, so my low is negative infinity. My upper, can't even remember what it was. 0.9. My mean is 1. Just click OK. But we want to change our standard deviation to be the square root. Forgot the square root. Okay, the square root of that. So that is on top. And on the bottom we got 6. I just stuffed it up. That is supposed to go there. So from that to 0.9, comma, standard deviation, mean, okay, 0.2490. So 0.2490. So in this case here, we're using a normal distribution to approximate a continuous function. And we get, there's a 25% chance that it takes him, the average time will be less than 0.9 seconds if he has 6 cups. And good luck on the exams.